This is the second video on G inverse. In first video, you see what is the G inverse and what is the idea of motivation behind the G inverse and why it is exists for every matrix and how do you find this G inverse. Now in this video I just classify this G inverse because for a matrix there are several G inverse. The G inverse may not be unique, and if it is unique, inverse exists, then it is unique. Now there is a very important theorem on G inverse. G inverse. This is lecture 2. So the important theorem is, if G is a G inverse of A, then rank of A is equal to rank of AG and is equal to rank of G. This is very important. Rank is not changing if I multiply by G, the G inverse. If I multiply a matrix by another matrix, then rank will be maybe reduced. Rank cannot be bigger. So we know if rank, always there is a rank of AB. We know there is important lemma result is that rank of AB, that is in my linear algebra videos, that rank of AB must be less than or equal to rank of A as well as rank of B. Similar, rank is also rank of B, and rank of AB is less than rank of B. Why this is so? This is clear because trivial to see that, because what is AB? Basically, AB is nothing but we know that there is a matrix A and there is a matrix B. So what is exactly AB? So AB, you can think like we know a matrix into a vector, like that a matrix into a vector from the right side is nothing but a linear combination of what? Linear combination of columns. So it is a linear combination of columns. We know that because this first column is only multiplied by the first element. The whole column multiplied with this element. The next column will be multiplied by the next element. You just check that what is the multiplication. So matrix into vector from the right side is just a linear combination of the columns. And matrix into a vector from the row vector from the right side, left side, it is just its first element will always multiplied with the first row, this part. That is, it is a linear combination of the row vectors. Now, what happened here? If you think this is a row of A, just some A as some collection of row vector, then single column vector of B gives a linear combination of row vectors, and the second column give another combination of row vectors. Remember, you can observe that the first column of B cannot affect the second column. It can't mix up. The first column effect of first column is not mixed with the effect of the second column. And similarly, first row of A doesn't mix with the second row of A. Now, this is interesting. So, it is actually list of. It is again a matrix. It's again a matrix, and this matrix actually a list of. So, it is a what? It is a column vector. So, it is some column vectors, collection of column vectors, and each column are what is it's in the right side. So it is a column, right? It's column. So each column is a linear combination of columns of A. Linear combination of columns of A. I just write in the wrong notation. So this is in the each column. Sorry. So each column. So the first column is nothing but a linear combination of the row column of A. In the second column of this AB is a linear combination of another linear combination of columns of A, the same column, same vectors. That means it's a collection of vectors which is linear combination of this column vectors. Now, what is the column space of A? What is the subspace spanned by that column? That is called column space. And the dimension of this column space, here dimension of this column space must be reduced, cannot be greater than that, because there is a linear combination of some. So there is a 7 vectors, 7 column vectors. Now here may be 8 or 10, but this is a linear combination of 7 vectors, and that 7 vectors is actually, if there are, say, 5 many independent vectors, say 5 independent, that means the dimension of this span by the 7 column matrix is 5. So rank of the matrix column or row rank same is the rank of this matrix is 5. But that rank of AB cannot be greater than 5, because that AB is actually subspace of that column space of A. So column space of AB is actually subspace of column space of A. That means subspace, the rank of AB cannot be greater than rank of A. And similar way, we can prove that the rank of AB cannot be greater than rank of B. Then we have to think that product of this AB, like rows, some collection of rows, and each rows is a linear combination of rows of B. So that's why this rank of AB is less than rank of A. So this is the outline of this proof. Now, why? But in this case, rank of A exactly equal to rank of AG. That means if we multiply it by some matrix, then that rank can be reduced, cannot be larger. But in this case, if you multiply by a G inverse, then rank will be intact, the same, can't be reduced. That means that linear combination, once this linear combination using the elements of G, then that linear combination does not change the dimension. That means it's not a proper subspace, it's exactly the same subspace. So column space, or if you multiply the right side, it's column space multiplied with the left side GA, it is a row space of A. It does not change the space. It's like a inverse. If you multiply by inverse, it just does not change your underlying vector subspace. So that is the idea behind the all this result. But you have to mathematically prove, you have to analytically prove this. The proof is like that. So this is the idea, and the proof is like that. So we know what? We know that rank of A is equal to rank of, what is this? Rank of AGA, because A is equal to AGA. That is a definition of that G inverse. We know that if G inverse, G is a G inverse, then AGA is equal to A. That is the definition, AGA equal to A. So that is the same matrix of same rank. But again, here it is AG. So AG multiplied with A, that means that should be less than or equal to what? Rank of AG, right? The product thing. So AGA A, so product that less than rank. But again, rank of AG must be less than or equal to, we can write just right hand side. Now again, the rank of AG is less than or equal to rank of A. Product material less than, cannot be bigger rank. Now rank of A less than or equal to something, less than or equal to something, less than or equal to A, rank of A. That means if it is A less than or equal to B, less than or equal to C, less than or equal to D, less than or equal to A, which actually means that A, B, C, D are all equal. So that's it all. Similarly, rank of A is equal to rank of AGA, and that is less than rank of GA, because AGA is A into GA. A into GA. So it is rank of GA, and rank of GA is again less than or equal to rank of A. So rank of A equal to rank of GA. So this is similarly we can prove it. So it is easy and it's very important theorem. Now the next one. So now the next one is the definition. A G inverse is called reflexive. A G inverse, sometimes a small letter actually. The matrix in the capital G, and we write small g. G inverse is called reflexive. It is called reflexive G inverse if you have extra property. If AGA equal to A, that is AGA equal to A, it is called G inverse. But in that case, it reflects not only AGA equal to G, it's also and G equal G. That is called reflexive G inverse. So if AGA equal to A and GA equal to G, then it is called reflexive G inverse. Now, what is the motivation? Why we put such a definition? We can put any definition. We can say this is this, that is this. If this is hold this condition true, then we can call this. We can say infinite definition we can put. But actually, we need some motivation. We can, if definition does not useful, this definition does not actually no need of that definition. So, what is the utility of this definition, and what is the motivation behind that? Now, you can observe one thing. It is an important note, so that if G is a G inverse, G is a G inverse of A, G is a G inverse of A, then the important part is GAG, that GAG is a reflexive G inverse of A, is a reflexive G inverse of A. It's very important. So once I have any G inverse, we can make it a reflexive. That is interesting. If you have someone give me any G inverse, number of G inverse is larger than the reflexive. So reflexive inverse is a G inverse. It is a smaller class. So once I have any G inverse G, then we can find another G inverse GAG, which is GAG may be equal to G, may not be equal to G. If if G is itself reflexive, then GAG is G. But if G is not a reflexive G inverse, then G not equal to GAG, but that GAG is a reflexive. So to prove GAG reflexive, what we have to exactly prove? We have to show two things. GAG, this is we have to prove this is G inverse. First, we have to prove it is a G inverse, whether it is G inverse or not. So you have to show AGA equal to G. So you have to prove that thing. So we have to show this first thing. First, we have to show A must be A. Just think GAG as a H. So why H is G inverse? A must be A. But this is easy, trivial. Why? Because this is nothing but AGA, then AG. And we know AGA equal to A because G is a G inverse. May not be reflexive, but AGA equal to G, A. So AGA equal to, again AGA equal to A. We used twice. So GAG is a G inverse. Next, we have to put is a reflexive. So to show it is reflexive, we have to show GAG. GAG is like H, say consider this as H. So H must be GAG. It should be able to prove that it is GAG. How do you prove? It is again, it's just clubbing this, thanks to associative law, you just club all these things. And AGA is equal to A, so it is GAG. Now again, this part, you just club this part, AGA equal to A, so it is GAG. So we prove it is a reflexive. So just we use twice again. So using that A is a G inverse, and we prove that GAG is a G inverse as well as a reflexive G inverse. So from any G inverse, we can find another G inverse which is reflexive. But if A is itself reflexive, we have nothing new. If A is reflexive G inverse, then we can't make it as a new reflexive G inverse. Then GAG equal to G. But if A is not a reflexive G inverse, then we find a G inverse which is reflexive. So this is the important result, and that motivates us to prove, to give such a definition. Now, this important theorem is this: let G be a G inverse of A. G inverse of A, then rank of A is less than or equal to rank of G. This is very important. So if it is a G inverse of A, then rank of A less than or equal to rank of G. So rank of A inverse, that is G inverse. So rank of A is less than or equal to rank of G. That is the interesting thing. So rank of inverse cannot be less than rank of A. Now, what is the proof? Proof is this. So let G is a G inverse, and we know if G is a G inverse, then what happens? Then rank of what? Rank of A is equal to, we know rank of A is rank of AGA, because it is just A equal to AGA, because A is G is a G inverse. Now, this is this, so it is again rank of less than rank of AG, and which is again rank of G. In the product matrix has a lower rank or cannot be bigger rank. So this is trivial. So rank of A less than or equal to rank of G. It may be less, it may be equal. Like if say your A is null matrix, then what is your G? G is in any matrix can be G. Say it is null matrix of order n cross n. Now any matrix of order n cross n is your any matrix. Take G is any matrix, because AGA, A is 0 here, null matrix is 0, null matrix. So it is true for all G n cross n. So for a null matrix, any square matrix is G inverse of null matrix. Now null matrix is rank 0, and any other rank is either 0 or greater than or equal to 0. So rank can be increased. But the idea is rank will be same if and only if it is a reflexive. This is the idea. So rank will be same. So another part is theorem that it's in the part 1 and part 2. We should not say another theorem. It is 1 and then 2. Rank of A will be equal to rank of G if and only if that G is reflexive G inverse. That we should not write that in this way. We should write G is a G inverse of A first. G is a G inverse. G is G inverse of A. Then rank of A equal to rank of G if and only G is reflexive. We can't say rank of A equal to rank of G, then G is reflexive G inverse. We can't say that. Rank of A and rank of B may be two different matrices. One cannot be G inverse or may not be G inverse of other. But if it is G inverse, rank of A equal to rank of G, and G is a G inverse of A, then G is reflexive. In the same way, if G is reflexive G inverse, then conversely, then rank of A equal to rank of G. So what is the proof? So we already proved that rank of A less than or equal to rank of G for any G inverse. So we have to prove for reflexivity is equal. So what is the proof? So first let G is a reflexive. So let G is reflexive. Since this is reflexive, what happens? So rank of G is equal to rank of GAG. So reflexive GAG equal to G. But again, it is rank of A. Product matrix cannot be bigger rank. Now rank of G less than or equal to rank of A. But we already proved for any G inverse rank of A is less than or equal to rank of G. So therefore rank of G is equal to rank of A. Now the conversely we have to assume that the two rank is same. So we already assume it is G inverse. So already we assume that. Now conversely, we already assume that AGA equal to G, A, this is G inverse, and as well as in extra condition we assume rank of A equal to rank of G. Then we have to show that this is reflexive. It is GAG equal to G, and that's needs slight work. That we just can't prove using that this rank thing and product thing. So what is the idea? So suppose rank is same. Now, if rank is same, first observe that the column space of GA is subset. We already show that the column space of GA is subspace of column space of G. Because you multiply it on the right side A, that means this GA is a list of is a collection of column vectors of G. So some column vectors, which each column vector is a linear combination of the column vectors of G. So collection of linear combinations of column vectors of G, and that is subspace of that column space of G. Now this is true for This is true for not only for G inverse, it is true for any matrix actually. Now, what happens then? Rank of GA is equal to rank of G. We already proved it. So we already proved it is rank of A. We already proved the first theorem that rank of G equal to rank of A. But we assume that rank of A equal to rank of G. We assume it, rank of A equal to rank of G. So rank of G equal to rank of G. Now what happened? Rank of G equal to rank of G. And column space of G is a subspace of column space of G. That means your dimension of GA, dimension of your that column space is less than or equal to dimension of your G, but we assume the rank is same, that means it is equal. Now what happens? If there is a vector space V, say V is a vector space and W is a subspace, and if dimension of W is equal to dimension of V, then what happens? Then we can say that W equal to V. A proper subset cannot have same dimension. Proper subspace cannot have the same dimension. The dimension is equal, then the subspace is itself. So this is the proof. So that means your column space of A is exactly equal to the column GA is equal to column space of G, because the dimension match. If the dimension match, then it may not be equal, but since it is subspace, that's why it's equal. Maybe two different vector space. The dimension may be matched, but may not be. It may be totally disjoint. It may be disjoint. Since it's a subspace, that must be equal. Now, what happened then? If column space of G equal to column space of GA, then what happened? So that means your G is a linear combination. The columns of G is a just a what? Therefore, G column space of G equal to GA means what happened? This is GA. What is GA? The columns of linear combination of list of linear combination of columns of G. And what happens? Then what can I say that there exists some matrix X such that G is equal to GAX. Yes. Why this is so? Since the column space is same, column space of G is equal to column space of GA, right? What is the meaning of column space of G? Column space of G means it is a span of the columns of G. And what is the meaning of column space of GA? It is span of the column space, span of the columns of GA. Now, any vector in G, any columns of G is a element of column space of GA. That means it is a linear combination of GA. That's why since G is itself the linear list of linear combination of GA, that means G must be GA equal to X for some X. So now we have this in the last line, GAG. You have to prove now GAG equal to that G. So GAG, we just put GAX, then A, then GAX, right? Now AGA equal to A, we know that AGA equal to A. Then that means GA what? What? How do you prove it? GAG equal to? Oh no, don't do this. Don't do this. GA. Don't put in the both sides. We just replace one G. Right. GA. You replace that G by GAX. Now GA. Now AGA is J. So it is A. Right, and AG is a G. So GAG. So this is the idea for reflexive, and reflexive I gives a new thing that your some G inverse exists. We know that G inverse exists, and there's some in this all set of G inverse. There's some special type of G inverse, whose rank is exactly equal to the rank of A. We can go much higher rank of A, but we are now into the same rank of A. Now still that reflexive inverse again is not unique, may not be unique. That means for a there is a several more than one, maybe one, only one. If it is inverse, obviously there is only one G inverse. There are several G inverse, reflexive inverse, and all of this exists. Because why it does exist? Because we know that there is G inverse exists, and once we have a G inverse, whatever it is reflexive or not, that GAG is again a reflexive G inverse. So we know the existence of G inverse, reflexive G inverse, and may not be unique, but we have some subclass of G inverse, which is one more extra property, that AG equal to A, GAG equal to G. That means it's in J inverse, and as well as it's the same rank of this if and only if condition of A. Now we have two more extra property, impose two more extra thing on G inverse. One is called minimum norm, and another is called least square G inverse. These are two different idea and two important idea. One is called minimum norm, and another is least square. Least square. So, and once we put this to condition, minimum norm and least square, we have to again see what is the motivation of this behind this, why we consider this. Actually the reflexive part is totally mathematical aspect, and this minimum norm and least square is from the statistical view. Once we have these two things, and we will show that this is exists, and again this may not be unique. So minimum norm G inverse may not be unique, least square G inverse may not be exist. But there is a G inverse which is least square. There is a G inverse which is minimum norm. There is a G inverse which is reflexive. Now the interesting thing is there is a G inverse which is minimum norm as well as reflexive, that we can show, which is a minimum norm as well as G least square. There is a G inverse which is reflexive as well as least square, and there is a matrix, a G inverse of a matrix, any matrix, which has all these things: reflexive, minimum norm, least square. And in that case, that G inverse is unique. We will prove that for any matrix, a G inverse exists, and that G inverse have three extra conditions: minimum norm, least square, reflexive, and such a G inverse is unique for every matrix. And this matrix G inverse called Moore-Penrose G inverse. So what is Moore-Penrose G inverse? Moore-Penrose G inverse is a G inverse which is minimum norm, least square, reflexive, and Moore-Penrose G inverse exists. Not only that, it is unique for every matrix. Now, what is just a definition of that? So definition is like that. So what is the definition? The definition is this. So it's called minimum norm. G is minimum norm G inverse of A, that is GA transpose equal to GA. That means GA is symmetric matrix. Now, why we'll take such a thing? That needs some results, some theorems. Why need something, and why it is important, and what is the utility of this? So if GA is symmetric matrix, that means GA transpose equal to GA, then we call it is minimum norm. But what is the name of minimum? Why this norm is coming from? It's just a symmetric thing. So it may call symmetric G inverse like that, but we are calling minimum norm. Why this name G minimum norm is there? So they need a result. So it is called minimum norm. And what is least square? Again, the least square in a similar way, G is least square G inverse of A, if that similar way it is AG now, AG transpose equal to AG. So AG is symmetric. So obviously there is a AGA equal to A is there, because it is first of all it must be a G inverse. AGA equal to A and AG A transpose equal to AG. So it is least square and GA transpose equal to G and AGA equal to A. Then it is minimum. Now why this least square term coming? You can see it is from the statistical point of view, least square. Least square is a least square estimation like that, and we need this result in linear model. So least square estimation of that, and that needs some this type of minimum least square G inverse and some Moore-Penrose G inverse. Now, in the next video, we discuss on these properties of this thing and all this Moore-Penrose G inverse. That what is the Moore-Penrose G inverse? The Moore-Penrose G inverse is fourth thing: AGA is equal to A, GAG is equal to G, GA transpose is GA, and AG transpose is AG. So if all these four property holds, then this is called Moore-Penrose inverse, and this exists and this is unique. We see in the next video.